Hello everyone. In the second part of our lecture on statistics and probability, our emphasis would be on probability distributions. And we'll be looking at two types of probability distributions. There are many other types, but our emphasis will be on just two. The first one is called binomial distribution. So from the name binomial, it means that there can only be two possibilities. Whenever you're assessing a probability, so there can only be two, and these two possibilities are called success and failure. So take note of that, or the outcomes are success and failure. I want to take note of the fact that in this context, success isn't in the grammatical sense. That something is good or that is what you want. No, it simply refers to what you aim or what you're targeting. For example, in the line of production, what you are targeting might be 40 products. You might be looking at the probability of 40 products in a batch of production. So your success, whenever you are calculating the binomial distribution, will be what? Will be 40. 40. What you're looking at, something that has a fault in it. So if we are to look at it in the grammatical sense, you say something faulty isn't a success. But when it comes to statistics, that is a target. So let's take note of that. So our x. So this is the formula we use. This is the formula we use. X is the number of times, the number of x. So x will be the number of your successes, the number of times for the success, for what you're targeting, and n will be the total trials, the number of times for, that will be for the success and the failure. So n will be that, and then the failures will then be n minus x. Remember, x is for success, then the total number of trials, within the probability will be n. So thus failure will be n minus x. And then p is the probability of the success, what you're targeting, and q. So p is the probability for the success, and q is the probability for failure. And so since within a probability, everything within a probability must end up to be 1 or 100%, it does means that your P plus Q will be equal to 1 or 100%. So your P plus Q is equal to 1 or 100%. So let's look at example 4 to want to make sense of this. It says the probability of getting exactly 2 heads in 6 tosses of a fair coin is given as this. So let's look at our formula, and then we try to do the calculation. So this is the formula will be given. Please take note, these are prime or factorial. So that is prime or factorial, which you can easily punch in your calculator. So take note. So we'll be using this. This is the formula we'll be using. So let's and the formula has been translated into this, but let's try and work it out together. So if I were to use that formula again, so we have our n, which is the number of total tosses or trials. So 6 prime divided by 2 prime. 2 prime, that's the number of successes, multiplied by the number of failures, which would be 6 minus 2, which is 4 prime, and then multiplied by the probability of success raised to its number. So remember, since it's 2 coins, so it can only be 50-50. You have 2 sides to a coin, 2 sides to a coin. So what that means is that we'll then have 1 over 2. So 50% or half, 1 over 2 raised to the number of success, which is 2. And then the failure will be the remaining 50%. Remember, we said failure plus success, everything adds up to the probability of failure and success, everything adds up to 1. So we have that. So then for failure, it will be 1 over 2 raised to power 6 minus 2, as we did here. So which is 4. So if we are to punch this in your calculator, your 6 factorial should give us 720, and then 2 factorial should 2, 4 factorial is 4. That is, so multiplied by half raised to power 2 is 0.25. Half raised to power 4 is 0.0625. If you calculate that, it should give us 0.23. But oftentimes, probability are better represented as percentages. So this is same thing as 23%. So what that means is that there is 23% chance of having 2 heads in 6 tosses of a fair coin. So there is 23% chance of having 2 heads in 6 tosses of a fair coin. So that's how we came about that. So oftentimes we use, like I mentioned earlier on, so it's used in quality control. So you want to see in your line of production, are there faulty products that you need to, faulty or products with defects? That's the other word, defective product, so that you can get rid of them. That's 1. Or 2, if the probability of having defective product is very high, you wouldn't want to release that batch of product into the market, because remember what we said earlier on, that part of a business being able to sustain itself is you need to do a quality control. So if the quality isn't good, if you have higher chance of defective product, you don't want to release that into the market. So it's used for quality control. And take note of this other formula we have here. Mu is the formula for mu is for mean, and then we have or average. So this is your mean or average of a binomial distribution, and then we have variance and standard deviation. So take note of this different formula. The next type of distribution, probability distribution, we'll be looking at is called normal distribution, and this describes how the values of a variable are distributed. How the values of a variable are distributed. This is your typical normal distribution graph. It's a bell-shaped graph. So this, I want to take note of the properties of this graph. The first thing I want to take note of is, just as we've seen for the in binomial distribution, we said sum of everything, all the probabilities, with all the probabilities, everything must be equal to 1. So in this particular case, we'll say everything under the graph, everything under this graph is equal to 1, or 100%. The probability when everything is summed up is equal to 1. The other thing we want to take note of is the midpoint. The midpoint is the mean. Meaning, for normal distribution, your mean is equal to what? The median. So your mean is equal to the median. So that's take note. So your mean is equal to the median. And then the inflections you have on both sides. So you have an inflection on the negative. You have an inflection on the negative side, and you have an inflection on the positive side. So the inflection on the positive side, those will be the values that are higher, that are greater than the mean. And the inflection on the negative side will be equal to the values that are smaller than the mean. So, and then you also have your delta, which represents the standard deviation. So standard deviation. So you want to look at how all the values vary from the mean, how all the values vary from the mean. So the standard deviation measures that the dispersion. Remember what we looked at in the previous class when we looked at measures of dispersion. So remember that. So looking at, if I were to look at these two data sets, A and B. So the one with, you see that both of them are bell shaped, but you see that one is wider, B is wider than A. So it means that B has a higher standard deviation. Also, B has higher standard deviation, or we'll say that it has higher dispersion, as we saw in the previous class. So that is what that's what these two graphs are telling us. But let's look at an example so as to make sense of this probability distribution. So typically, when it comes to your normal distribution, it's difficult to calculate. So what we do is we standardize in order to simplify the calculation. We standardize in order to simplify the calculation. This will make sense when we look at example 42. So in order to do that, we say that the standard value, what we standardize is called Z, and remember X, that would be so we have X would be the data we are looking at. Mu, that is your mean. We've said that, and we've said delta, that is our standard deviation. So let's look at an example in order to make sense of that. So example 42. Suppose a family income in a town are normally distributed. Take note of this. Anytime you have a question on normal distribution, this will be mentioned there. So then you know that it's normal distribution that you're using to calculate here. So you won't be able to, you shouldn't be able to confuse it with binomial distribution. Remember what we said in binomial distribution. There are always two possibilities, yes or no, success or failure, defective or non-defective. So there are usually two possibilities. But when it comes to questions of normal distribution, you are going to find this phrase there: normally distributed. All right, so we have the mean value is 1200. So that would be our mu, 1200, and standard deviation would be 600. Take note, earlier we've said earlier on that this is the formula that we'll be using. So take note of that formula. So remember we said for normal distribution, it's difficult to calculate. So what we do is standardize. So that means we have two values here that we need to standardize. So we've gotten the mean, we've gotten the standard deviation. Let's look at the question. It says, what is the probability that a family has an income between 1,400 and 2,250? So what this means is we have two x values, x1 and x2, and we need to standardize both of them to z1 and z2 using the formula that we have. Let's move on to the next page and try and work it together. I've solved it here, but I want us to just look at it together and use graphical representation to make better sense of it. So for z1, so that will be, so if you look at the formula, so for z1, we remember for Z1 is from X1. So that would be let's look at that 1,400 minus 1,200 divided by 600, and then Z2 will be 2,250 minus the average 1,200 divided by 600. So if you do that, the value we get will be 0.33. So this gives us 0.33, and this gives us 1.75. So take note of that. So these are the standard values. These were the original X values. So these were the original X values, X1, X2. But these are now the standard values, Z1 and Z2. So the next thing you do is you use this chart that will always be provided to you. So for take note, for 0.33, you start with the column, and then before you look at the row. So for 0.33, we start with 0.3, and then 0.3, we look at point. So this would be 0.3. So that means the equivalent value on the graph, the equivalent value in the normal distribution graph will be 0.1293. Let's write that down. So 0.1293. And for 1.75, 1.7, we start from the column 1.7, and then to get 1.75, we trace it to 0.5, so it should be 0.4599. So take note. So those will be the equivalent values on the graph. Let me just draw. Let's draw the graphs to make sense of what these values imply. So I'm going to draw two, so as to show the normalized values. So I want to show that. So remember, we said the middle point, that is where the average value will always be. So 1002 will be here in the middle. And then you remember we have two X values. So X1, 1004, since it's greater than 1002, it will be somewhere here. The other one, 2250, will also be somewhere there. So remember, this is the middle point. So that will be somewhere. So those two values are there. So we have 1214 and 2250. So what do these values mean in terms of the probability distribution? Let's look at the other graph here. Same thing, but we now want to convert these values here. So it means that if you are to remember, the middle point when it comes to the probability is the middle point is equal to 0. So the value for Z1, 0.1293, that means everything from here, there. Remember where 1004 was or should have been. So everything from there, so everything here is equivalent to 0.1293. And then for 2250, remember our reference point will always be the middle, 0, from where the mean should be. So for the second one, 0.4599. So it will mean that would be from here to somewhere there. So 2250 should be somewhere here. So that means everything from here there. I want to take note of this. You see we have carefully drawn it. Just for you to get it, you see that I marked it at a point there. I didn't mark it at the end at this point. The reason being that, as we described in the previous slides, the mean is also the median. So it divides the graph in half. So it means everything in here should be equivalent to 50% or 0.5. Same thing here. Everything should be equivalent to. So that's why you see here, from here, there, it will be 0. So from here, there, that will be 0.4599. But the question is asking us between 1,400 and 2,250. So it means that the area we are looking for, so we have for 1,400 is from here there. For 2,250 is from here there. But we are looking for the in-between. So we are looking for the in-between, between 1,004 and 2,250. So how do we get that? We just, based on that, since it's the in-between value, it will just be 0.4599 minus 0.1293. So that gives us 0.33, which is equivalent to 33%. 33%. So the answer will be the probability that a family earns between 1,004 and 2,250 is 33%. Let's try to look at another scenario. Remember, this question says between 1,004 and 2,250. Let's look at another scenario to say between $1,000 and 1,004. Let's still use the same. The other one, between $1,000 and $1,400. So let's do the same thing we did in the previous case. So remember, you calculate the Z values. So Z1 will be similarly as we did here. So it will be 1,000 minus the mean 1,002 divided by the standard deviation. And then for the other one, Z2 will be 1,004 minus 1,200 divided by 600. So if we are to calculate that, this will give us minus 0.33. Take note of the negative and how you are going to interpret it in the graph, and this gives us positive 0.33. All this is just telling us is that if we're in the graph, I'm going to draw. Let's draw the two graphs again. So remember, in the first graph, let's put the values, the x values. So you have x1, x2. So in the first graph, the x value, the mu value will be 1,200. Remember, that's the average. 1,000, since 1,000 is less than 1,002, where would it be? It would be on the negative side. So it will be here. So that's why you have the minus value there. And then 1004 is greater than 1002, it will be on this side. So it means that the areas, when we're looking at between 1000 and 1004, we'll be looking at this entire area. So unlike what we did in the previous one, we'll be adding, because it's this area plus that area. And take note, we've said the only thing this negative implies is that it's on this side of the inflection. That's all it means. So you see that as we move on, it will not be removed. There wouldn't be any subtraction. It's only showing us that it's on the negative side because it's less than 1002. So if you were to go back to our chart again, so for 0.33, so same thing, so it's going to be the same value, 0.1293. So same thing that we did earlier on. So we have a 0 value for 1000 for the mean, and then for 1000 the graph, for 1000 this area will be 0.1293, and this area as will also be 0.1293. So this is for the 1000, this is for the 1000, and that is for the 1400. So since the question is between $1,000 and $1,400, so it means we are looking at this entire area. So this entire area, so it does means we add 0.1293 plus 0.1293. So we add the 2, giving us 0.26, which is same thing as we say 26% probability. So that's how we do that. So that brings us to the end of this particular topic. And please, if you have any question, don't hesitate to drop me an email or a WhatsApp message, and I'll be willing to help you out. And you can also contact the teaching assistant as well. Thank you. All the best.